Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list published on February 10th, 2026, just yesterday. It introduces a training-free framework that allows large language models to dynamically switch between different cognitive mindsets step by step, improving overall accuracy by about 5% compared to the strongest existing baselines. The paper is titled Chain of Mindset: Reasoning with Adaptive Cognitive Modes. And as we'll see later, the way this method mimics human flexibility in problem solving has some really significant implications for complex reasoning tasks. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 provides a performance overview comparing the chain of mindset framework against 7 baselines on the QN3 model. This radial chart covers 6 diverse benchmarks, encompassing mathematics, coding, and spatial reasoning. The chain of mindset, shown as the outermost dark purple bars, consistently takes the lead. For instance, on the AME25 math benchmark in the top right, it achieves over 73% accuracy, substantially outpacing the nearest competitor. It holds a similar lead on the live code bench at the bottom, confirming that adaptive switching works across varying domains. So Figure 2 illustrates how this new approach differs from standard methods. At the top, Panel A shows single-mode reasoning, like traditional chain of thought, where the model uses one fixed thinking style from start to finish. In the middle, Panel B depicts static strategy selection. Here, the model picks a strategy at the beginning, but cannot change it later. Finally, Panel C presents the chain of mindset. Instead of locking in one path, the system dynamically selects the best cognitive mode, such as algorithmic or spatial, at every single step, adapting as the reasoning evolves. Figure 3 details the internal architecture that makes this flexibility possible. On the left, the meta agent acts as an orchestrator, effectively deciding how to think rather than just what to think. It analyzes the current state, dispatches a specific task via a mindset call, and then synthesizes the returned results into a key insight. On the right, the diagram lists the 4 specialized experts: divergent, algorithmic, convergent, and spatial, which handle the actual reasoning. Importantly, the yellow boxes mark the context gates, which filter information entering and leaving these modules to prevent the context window from getting cluttered. Having seen the architecture, Table 2 now presents the concrete results when using Gemini 2.0 Flash as the base model. The bottom row highlights that chain of mindset achieves the best overall accuracy at about 52%, consistently outperforming the other methods listed above it. This advantage is particularly stark in multimodal tasks. For instance, on the maze benchmark in the second-to-last column, it hits 84%. Even on difficult math problems like AIM25, shown on the left, it maintains a clear lead over the baselines. While the previous table focused on Gemini, Table 1 switches the backend to the QN3VL model. The bottom row highlights the proposed method, which again secures the top spot, with an overall score of roughly 63%. This advantage is most dramatic in the AEME25 math column on the left. Here, the model achieves over 73% accuracy, surpassing the strong React baseline in the middle of the table by exactly 10 points. Alright, Figure 5 examines the trade-off between accuracy and efficiency. In the left chart, Panel A, the yellow star shows that chain of mindset achieves the highest accuracy, about 63%, at a moderate cost. By contrast, the blue square for tree of thoughts on the far right consumes over 140,000 tokens, but performs worse. Panel B, on the right, reveals why the design works. The red cross shows that removing the context gate causes token usage to nearly double while accuracy drops, confirming that filtering information is vital. Wrapping up, the big takeaway is that flexible thinking beats rigid strategies. By dynamically switching cognitive modes, like moving from spatial visualization to algorithmic execution, this framework mimics human problem solving to significantly boost accuracy without retraining. It suggests a future where AI agents are defined not just by what they know, but by how they choose to think. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.